That's a fun sound. Okay, so I have to use the microphone so that the recording picks me up. Thank you, Fred. It's good to see you all here. So as Fred said, I'm Phil Ilten, and I'm going to give you a little bit of an introduction about myself, not as a person, but as a physicist, so you maybe know where my areas of expertise lie. So if you have questions, you know which questions I might be able to answer or what questions I might not be able to answer. So I am faculty at the University of Cincinnati, and first and foremost, I'm an experimentalist on LHCb. So on the LHCb experiment, which is one of the experiments out on the LHC. It's one of the smaller ones, but it is on one of the beam interactions, and it's a dedicated experiment specifically for B physics. So that is kind of what I would call my day job, I suppose, although it's becoming more and more blurred over time. And some of the things that I do on CODA or on LHCb is I do searches for dark sectors. So this includes things like dark photons, axions, things like this. Displaced signatures, very light signatures that the LHCb trigger can pick up. Precision electroweak physics, so things like Z cross-section measurements, W cross-section measurements, et cetera, and then jet substructure measurements as well. And I'm going to talk about one of those measurements later in this lecture today in the context of Monte Carlo and why having good Monte Carlo is important. Then in terms of other things I do, I'm the spokesperson for this Codex Beta demonstrator. It's a long-lived particle detector, and it's a demonstrator for it being installed just off to the side of LHCb. It consists of resistive plate chambers, and it can look specifically for long-lived signatures. So for example, if you might have a dark sector Higgs, or if you have some sort of heavy neutral lepton or something like this, it could be produced at the LHC and then be picked up in this detector, which is a relatively background-free type of detector. So I spend some time on that as well. And then the thing that brings me here today is my involvement with Pythia 8. So I'm actually really heavily involved with Pythia 8. I'm the lead technical developer for that, which means that I need to make sure that everybody's merge requests go in, that the code's all relatively good quality, that we pass tests, et cetera. So you'll see that a lot of my lectures and a lot of tutorials that we do are going to be very code heavy. So this is why it's coming from this part of what I do. Some of the things that I've done within Pythia 8, the tau decay mechanisms through helicity correlation matrices, Corconia production, both in the hard process and the parton shower. We'll talk about this a little bit later. And then some non-perturbative model stuff. So coalescence models, hadronic rescattering. If you don't know what these things are, don't worry. I will talk about some of them more later on as we get through these lectures. Then some of the other things, there's this MLHAD group, which stands for Machine Learning for Hadronization, which actually kicked off this MC-Gen group. The MLHAD group really is trying to understand the process of hadronization, so the process of quarks and gluons coming together to give us bound particles through machine learning. We have one of our founding members of MLHAD in the back, Tony. That's Tony. Tony will be doing some of the tutorials, leading some of the tutorials later this week, and is a machine learning expert as well as a Monte Carlo expert as well. So it's very good that we have Tony with us this week. So that's the MLHAD group. We'll have two other people joining us. We have Manuel, who will be joining us tomorrow. He's also in the MLHAD group, and we also have then Rekab joining us today. His flight was delayed, but he'll be joining us as well. All part of the MLHAD group, all experts in machine learning and Monte Carlo. So you are in good hands because my machine learning, while I may be passable, Tony's is much better. So this last thing then is this MC-Gen group, which I want to talk a little bit about. MC-Gen stands for Monte Carlo General Education Network. And it was designed as a prototype kind of education network that's very similar to MCNet in Europe, for those of you who might be familiar. The goal of MCNet is basically to build a collaboration of Monte Carlo authors and to have students learn Monte Carlo techniques through that network. MC-Gen is a blatant copycat of that here in the US, and we have funding for 3 years. To that end, there are a number of studentships which are available. So if any of you are interested in any of this, I highly recommend that you take a look at this link. This link should be on the slides on Indico, and it will bring you to this page here, which is the MC-Gen page. What you'll see is that there's this stuff about schools. So CTEQ was very, very gracious and partnered with us on this. Or I should say, we partnered with them in the fact that we slotted ourselves into their schedule. But then there's also this fellowship thing here, which I just want to advertise very briefly, which is that these are 6-month studentships where you basically can come work at one of our sites. So either Berkeley, Fermilab, or Cincinnati, and you can work specifically on Monte Carlo work. So this is an opportunity that is out there. So if any of you are interested, please do come talk to me, take a look at this page as well. So that's that advertisement over. Okay, so I want to talk about now what the curriculum is going to be from the MC-Gen side of things. And so I've given this block here, this block schedule that I think, Fred, you put this together, but I just want to highlight some of the things here for this. So the first is that we have everything in this lovely magenta color here. These are the lectures that we're going to be giving. So unfortunately, you're going to hear from me a lot. I'm giving 3 lectures. I'm giving these 3 Monte Carlo lectures. So these introductory lectures to Monte Carlo techniques. I'll give you a brief overview of what's going to go into each one of these in a second, but I want to go on to the rest of the program before I do that. Then we have 2 lectures on machine learning. One is more of an overview and an introduction. One is more advanced methods. Both of these are going to be given by Manuel. So this is what we have for the lectures for machine learning. Then a lot of this is going to be based in tutorials. So every one of these red blocks corresponds to a tutorial block. So tonight we're going to do just a general introduction to Pythia. The reason we use Pythia opposed to some of the other Monte Carlo generators is not because Pythia is better. It isn't necessarily for certain things, just because all of us who are teaching these tutorials are more familiar with Pythia. So that's the reason we do it, and I just want to make sure that's clear to everyone. So we have this Pythia introduction here. Then we've got random number generation tomorrow. You're going to learn more about random number generation probably than you ever wanted to, but it's really quite important for Monte Carlo. Otherwise, you can get yourself in trouble, as we'll see probably in this lecture today. Then we're going to talk about sampling and integration. This is the 3rd lecture here, or sorry, the 3rd tutorial here. So again, these are not introductory, these are foundational Monte Carlo techniques. Then on Wednesday and Thursday, this is when the fun really gets started, bless you. This is when the fun really gets started. We're going to then get into the HEP-specific part of Monte Carlo. So we're going to talk about matrix element generation, matrix element integration, parton showers, hadronization. So that's all going to be on Wednesday. And then we'll transition into the machine learning side of things. We'll cover regression, classification, auto-differentiation, and then neural nets. So there's quite a bit on the menu. There's a number of detailed notebooks out there. And so hopefully we'll get through a lot of the material, but if we don't, the notebooks are still there for you to peruse. So in terms of the notebooks, the way that we're technically going to handle this, I just want to make sure that everybody's set up for this. Fred already told me that for some of the XFitter work, you did Colab, which is great. All of the tutorials are going to be through Colab. You can access the links here at this README. This repository contains all these tutorials, so if you ever want to access them later. This is then mirrored onto a GitHub site, which then gets picked up by Colab. So that's the process of how this is done. But the links to open up any of these notebooks on Colab are given here in that README. So if you want to access any of them. What I will do, though, is on the Indico page, as these tutorials come up, you'll see the links for the tutorials come up. So for example, I don't have it up, so I'm not going to show you. But the link for the Pythia tutorial is up already on the Indico. This page looks like, if this would go away, we'll put it down here. Looks like this README here. So you see that we're basically factorized it into 2 things here. So we've got these notebooks here, and we've got these machine learning notebooks here. Not all of these are in their final form yet. So if you're looking at something and it looks like it's not in its final form, then it's probably not in its final form. We've been putting a lot of work into getting these notebooks together, but it's a lot of material. So we request that you bear with us as we go through these things. There may be errors, and then it will be a learning experience for all of us. In any case, though, if you click into one of these, you'll see that it brings up the notebook, and then you have a Colab notebook sitting here, and then you can go through it and do it. Don't ruin the fun for the tutorial session and do it while I'm giving my lecture, please. All right. So that's kind of the technical things of how this is all going to work. So let me go back to this here. I want to give you a few resources up front on the Monte Carlo side of things. These lectures that I'm giving, these first 3 lectures, they're heavily based on other lectures. So they're based on previous lectures that I've given at CTEQ schools, but they're also heavily based on lectures from a number of other people. First and foremost, Torbjorn Sjöstrand, who is the kind of progenitor of Pythia. He has some very, very good material available at that link there, where a number of talks that he's given are available, and they are very good talks. So I highly recommend that you take a look at those talks if you get a chance, or if you're confused about anything. Then there are some very good lectures from previous CTEQ summer schools as well. For these CTEQ schools, a number of different lectures are brought in on the Monte Carlo sides. So there will be people from Herwig, there'll be people from Sherpa, and there are very, very good perspectives from these other generators that are given as well for these summer schools. So I strongly suggest that you take a look at those if you get a chance. Then there's this QCD and Collider Physics textbook. How many of you, just quick show of hands, how many of you know this already? Okay, a few of you. This is an excellent book. It is called the Pink Book because when it was originally published, it's pink. But it is a very, very good introduction to QCD and Collider Physics, particularly in the context of Monte Carlo. So I would highly, highly recommend this. Then there's the Pythia 6 manual. The Pythia 6 manual actually has a lot of the Monte Carlo side of things, so the Monte Carlo techniques. Some of the details of the implementation for how things are done are given in the Pythia 6 manual. It can be really useful for that regard. I haven't put up the Pythia 8 manual. The Pythia 8 manual is also useful, but really the Pythia 6 manual is the one that I would say to go to. And it really pains me to say that because I helped write the Pythia 8 manual. So, okay, so then there's some other ones as well. There's this general purpose event generators for LHC physics. This is by Andy Buckley and a bunch of other Monte Carlo physicists or phenomenologists. It is a very, very good overview of all of this. So I would highly recommend taking a look at that if you want to overview. And then there's this introduction to parton shower event generators, of which we have a adaptation of a notebook in progress, not ready quite yet, which we will be giving later in the week. But the original source of it, which is really quite involved, is this by Stefan Hucke, who's a research scientist out at Fermilab. Highly recommend this. Stefan is an incredible particle physicist in the Monte Carlo world, and he knows this stuff about parton showers probably more than anybody else. So I do really recommend that resource as well. Okay, so I think that's everything that I wanted to cover for resources. So let's give an overview then of what we're going to talk about in these lectures. So we have 3 lectures on Monte Carlo. The first one is an introduction and Monte Carlo techniques. So first of all, introduction as to why and how we use Monte Carlo in a particle physics setting, and then some of the technical nitty-gritties, which we will then cover more in tutorials later on. Lecture 2, it's going to be matrix elements and parton showers. Lecture 3, multi-parton interactions, hadronization, and non-perturbative effects. So kind of all the non-perturbative stuff will be shoved into lecture 3. You'll notice that in terms of the way that the tutorials work out, we're going to be lagging behind in the technical tutorials from what I cover in lecture. That'll be okay. It'll give you a little bit of time to digest the information that I've given you in lecture, so that when you revisit it again, it'll be maybe in your memory a little bit better, or it will allow you to recall it a little bit better. So I'm not too worried about that, although we'll see how it goes. Okay, so in any case, lecture for today, introduction and Monte Carlo techniques. So without further ado, let's start off with what Monte Carlo is. So we hear this word Monte Carlo, it's used a lot, and the question is, well, what do we mean by Monte Carlo? And so I put up my kind of best few words summary of it here. And the idea is using random sampling to calculate some sort of numerical result for problems that may or may not be deterministic. So you may have a deterministic model. For example, you might want to know what traffic flow patterns are like, and you could use a deterministic model for every single car that goes through that traffic flow, and you could step it through. Or you could use some sort of random sampling to do it instead, because this might make it fast. Or, for example, you can use it for truly probabilistic types of things. So in particle physics, of course, when we collide particles together, we do really have a probabilistic event that is produced. And so in that case, random sampling actually is quite natural. Now I've got this image here grayed out because this also is another very important use for Monte Carlo, and that is in image generation. So any of the movies that you watch nowadays that typically have any type of visual effects, or whether they're entirely computer generated, like Finding Nemo here, almost all of them, not all of them, but almost all of them use Monte Carlo methods to generate those images. So they will produce some sort of model, and then rather than just doing ray tracing from a normalized grid across all of the kind of space of that model that they instead have their light sources, and they do Monte Carlo sampling from those light sources. So for example, here, they'll have some sort of light source in this room, and then they'll take individual rays from it, trace it through their entire model, have all of the physics involved, whether it's diffraction or diffusion or whatever it might be, And then they will have a camera where those rays then are incident, and they do it with Monte Carlo sampling. And so, for example, this is where they do it with a very high level of Monte Carlo sampling. This is where they do it with a much lower level of sampling. And you can see here how that Monte Carlo actually enters into here. So you can see each of these points basically corresponds to a randomly generated ray that is traced through the entirety of that image. So it is not just particle physics where we use Monte Carlo techniques. But what about Monte Carlo in the context of particle physics? Why is it so important? Well, there are mainly three reasons why Monte Carlo is really quite important, and particularly why we use it in this idea of event generators. So a Monte Carlo simulator that can give you the effective production of particles being collided, whether it's at the LHC or the Tevatron, or whether it's at Bell 2 or wherever it might be. So there are a few reasons. The three reasons are as follows. The first is that we can connect a perturbative regime where we can actually use perturbative QCD or perturbative QFT in general, where we can actually make these calculations, to a non-perturbative regime where we cannot use perturbative QFT any longer, specifically in the context of QCD, where we reach an energy regime where we're no longer having convergence at all. So this is the first kind of reason that it's really, really quite useful. It allows us to connect these two regimes. Another reason that it's super useful is from the experimental side. It provides us complete events with final particles, which means that you can calculate any type of observable that you want. You don't have a bespoke calculation for each observable you're trying to measure. So for example, you can go and you can do an analytic calculation of, let's say, rapidity of Z production at the LHC. If you do that, but then you want to go to some other observable, then you're going to have to change your code. With Monte Carlo event generators, you get it all in one because you get those final state particles out. So you can go to any type of observable that you might possibly want. So this is really quite important, not only on the theory side, but then even more important on the experimental side. The reason being, as experimentalists, we want to understand how our detectors work. To understand how our detectors work, to understand what collisions from nature would look like in that detector, we want to have a simulation of that. We want to have a simulation of the particles passing through that detector, which means that we need to have the initial generation of those particles to begin with. And so this is what allows experimentalists to characterize and design detectors, is event generators like this. Then the last one is one that's not to be underestimated, which is that this is a very robust way to perform high dimensional integrals. Even analytic calculations where they're coded up, if they have to do integration, so if, for example, you code up something and you're not using a general purpose Monte Carlo event generator, but instead it's a specific observable you're looking at, so whether it's DY turbo or something else, they almost always will use Monte Carlo integration of some sort because it's very efficient as you go to high dimensionality. And in particle physics, we have very, very high dimensionality, as we saw from the previous lecture. Okay, so let's start off with this connection between the perturbative and the non-perturbative in the context of how these event generators work. So we start off with beams, and these beams have parton density functions. So this is my, and I should actually say, I think this is Torbjorn's little cartoon of what this looks like. He's got a proton sitting over here, and then he's got a proton sitting over here as well. Hey, Recob, it's Recob. So also ML had. Glad you can make it with a flight. Okay, good. So proton here, proton here. Or if you're working at the Tevatron, it might be an antiproton. This is supposed to then kind of correspond to the parton density functions that you have inside, or the parton distribution functions that you have inside, and you have these two collide. At this point, we don't really know how to connect these up. So we have then some sort of hard process that we do know how to calculate. So for example, we might have this type of hard process here, where we have an up quark taken from one proton, and we can take it from this proton because we know the PDF of the proton. And we might have a gluon taken from this proton here. And then we can have a W produced, and we can have a D quark produced as well. Okay, so this gives us our hard process. We can calculate this using the factorization theorem if we know what this PDF is, if we know what this PDF is, and then we can do the QFT to get this out. But this is a slight problem, which is that the scale of these protons and the momentum of these protons is such that this hard process is very far removed from it. So we have to somehow connect them up because this right here will not just cut it. So that means that we need to do something else. Before I talk about that, though, I'll note that we have this W sitting here. A W is not what we're going to see in the detector, of course. The W will decay. So typically in Monte Carlo event generators, what you'll do next after you have this hard process and after you have these beams set up is that you will then decay this W. And so in this particular case, we call these resonance decays, where it's something that happens immediately after this hard process. We have this W decaying into a charm and an anti-strange. So now you see that we're sitting here with quarks here and a quark here, but we still have this disconnect between the actual energy scale where we'll see hadrons in the event and the energy scale of these protons. So there are some other things that we need to do here as well. So the next thing that we're going to do is initial state radiation. This is what we call a space-like parton shower. The idea is that you start at this hard process here. You start at this hard process here, and you use these PDFs, and then you also use your knowledge of the splittings of QCD, so specifically what we know from DGLAP, and you evolve these things backwards to the proton. And you do that by introducing these emissions. So for example, as we go along here, we say, aha, we actually didn't just get this quark right here. We didn't just get this up quark here by itself, but rather it radiated a gluon before it gave us our hard process. And for example, aha, this gluon actually radiated off of some other quark that we had in this proton here. And so that way we take this hard process here, which is at a relatively high scale. So let's say the electroweak scale, so let's say 100 GeV, and then we can evolve it backwards to these protons here. So this is our initial state radiation. We call it a space-like parton shower because it goes backwards in time, which makes it this space-like type of parton shower. Then we have final state radiation, which is a time-like parton shower. Same idea. You basically use your knowledge of QCD and the splittings of QCD to go from your hard process here to a lower energy regime for your partons. So in this particular case here, we have this W. This W with a resonance decay gave us a charm and an anti-strange. This strange then radiates a gluon. This gluon then splits into two more gluons. This can continue onwards and onwards. This charm quark here again radiates some gluons. You get the picture here, hopefully. We keep on doing this evolution until we get to an energy scale that's low enough that this perturbative regime, where we basically do this DGLAP evolution, but through Monte Carlo methods, no longer is valid anymore. So in other words, these splittings that we do here, we can no longer calculate them using perturbative QCD. So that brings us then to another part of this, which is multi-parton interactions. So we have, in this event here, we have this hard process. We have this initial state radiation in green. We have these final state radiation in blue. But when these protons collide, if they're close enough, we're not just going to have one parton in this one and one parton in this one interact. Instead, we'll have a whole bunch of partons interact. So for example, here we have two gluons scattering off of each other, and that will produce some additional activity in this event. These types of multi-parton interactions are critically important for any type of measurement, particularly in the context of LHC. When you produce a very, very high energy process like this, okay, this is maybe not high energy for LHC, but a relatively hard process, it means that the impact parameter between these protons is relatively close. So the probability of having more partons scatter goes up, so you get this pedestal effect, where you have more event activity in these types of hard events that you're looking at. So it's very important that you get this right. Otherwise, what you're generating is not going to give you a realistic simulation of what the event will look like. Of course, with multi-parton interactions like this here with these gluons, this is not the final story. We still need to add on to that initial state radiation and final state radiation as well. So that gives us MPI radiation. So we do ISR and FSR on top of that. And so then we start to get a very, very complicated diagram from here. And that brings us to the final partons and beam remnants. Before I talk about that, I do want to mention something here, which we'll talk about in another lecture later, which is that this step here, MPI, radiation on MPI, initial state radiation, and final state radiation, all of these are done in an interleaved fashion. So in other words, we don't just do all of the final state radiation first, or all of the initial state radiation first, or all the MPI first. Instead, we have an ordering variable, and we interleave them with each other. So we might do an FSR, then an ISR, then an MPI, then another MPI, etc. So there's an ordering as to how these things are done. but we'll talk about that more later. Okay, so we've gotten to the point now where we've pretty much gotten as realistic as currently as we can an interaction between these two protons, except we still have this problem that everything that we're sitting with here is a parton. It is a quark, it is a gluon, or if we have leptons, they'll be sitting there, of course, or photons, they'll be sitting there as well. Those are okay, but anything that's a parton, anything that's got color charge, this is going to cause us a problem because, of course, we don't see this in nature because of confinement. So we somehow need to get all of these partons into the actual hadrons that we see in the detector. So how do we do that? Well, we work with the final partons in the beam remnants, which is this. So I've cut out all that intermediate stuff, and this is what we're left with. So we're left with a bunch of gluons, we're left with some quarks, and we're left with these protons, but now they're depleted somewhat. So they don't have the same structure as they did before. So then what we do is we try to connect everything up with what we call color connections. And we do this in called the large color limit, where instead of just working with our 3 colors, we instead say every time that we have a color-anti-color pair, we give it a new number. And this works very well for Monte Carlo for a number of reasons, which I'm not going to talk about here. But the idea is that you take those numbers and you can connect everything up. So you have basically color lines between everything in your event. And that will look something like this. So for example, this quark here will have some sort of color. This gluon will have color anti-color. That anti-color will correspond with this quark. Then the color will correspond with the anti-color of this gluon, and so on and so forth. And you can trace all of these color connections around. So we have a color connection like this. We have a color connection like this. We have a color connection like this. So for example, this quark is color connected up to this proton here. There are a number of different models of how you can make these color connections. Some of them are based on minimizing energy. Some of them are based on some loose guesses on QCD rules. It's still a very open subject as to how you do these types of color reconnections. Okay, once we have these color connections though, then we need to take these color connections and produce hadrons from them. And to do that, we use a phenomenological model. And in Pythia, what we do is we have these color strings, and then we use the Lund string model where we effectively think of these partons pulling away from each other. And as they pull away from each other in momentum space here, as they're moving apart, then we have quark-anti-quark pairs being produced. And this is something that we're going to go over in detail in one of the tutorial sessions. So this is going to be on Wednesday, the second tutorial section. This gives us then a whole bunch of hadrons. So what do I mean by this? Pi plus, pi minus, pi zero, rho, things like this. You can also get baryons out, proton, lambdas, things like this as well. This gives us all of these types of things that we want in terms of being able to see it in the detector. This is still not the entire story, because of course, if we have a rho meson, that rho meson will decay relatively quickly to the point where experimentally it looks like it's prompt, because it is from an experimental perspective. And so that means we need to do the decays of all of these particles that are produced in that hadronization. And we can do this, we can calculate it with matrix elements when possible. So sometimes we can use perturbative calculations, sometimes we can't. But then we get all of our final state particles coming out. Now, of course, something that's important to note here is, what do we really mean by final state particle? For example, if you have a pion, so let's say a pi minus, that pi minus can, of course, decay, and it will decay. But in most of the LHC experiments, we treat it as a stable particle because it's so boosted that it won't decay within the detector. Sometimes it does. This is what we call decay in flight. It messes up analyses when you try to go do them. But the important point here is that you have to have a definition of what you mean by stable in the Monte Carlo generator. So you might say, I only decay particles up to a certain lifetime, or boost within a certain region of phase space or something like this. This is another view of what this might look like. So this image here, I think, really steps us through the entire process quite nicely. This image here, this actually comes from the Pythia 8 manual. We're rather proud of this image. There's a lot going on here, but I want to just walk through all the steps again, so you're all kind of used to seeing these types of schematics. So here we have the hard process. So this is some sort of hard process that's produced. In this case, I couldn't tell you 100% what it is because the types of lines that we have here don't tell us exactly what it is. We have this hard process connected up to the beams here. They have initial state radiation. So that initial state radiation is given by these blue lines here. We then have kind of our initial gluon line here, which is given by this black line here. We have additional MPI, which are given by these blobs here. We then have FSR, so final state radiation, which is given by these red lines here. And then we have these strings, which color connect up all of these kind of partons that we have here. Then there's this kind of shell right here. That's when we hit the hadronization process. After the hadronization process, we then get all of these particles that are produced. These are these blue ones. These are the primary hadrons, so things like pions, rhos, et cetera. And then after that, we have secondary hadrons, which come from the decays. And then here, there's an even additional thing, which are these hadronic reinteractions. So this can happen if you have Bose-Einstein correlations, or when you have particles interacting through hadronic rescattering or something like this. So the idea is that you start off at some high energy scale here, and then you evolve outwards in terms of your energy scale if you kind of ignore these beams a little bit. Okay, so this is general overview of how these Monte Carlo event generators work. So there are a lot of Monte Carlo event generators out there, and I want to give you an overview of what is available. How many of you have used a Monte Carlo event generator before? Quick show of hands. So a lot of you, which is good. How many of you have used one of the ones on the screen right here? Many of you, good. So there's a lot of options out there. This is not exhaustive whatsoever. This just gives you a foothold if you haven't seen some of these into why you might want to use some of these, how you might want to use them, what strengths they might have, things like this. So there are kind of two categories of Monte Carlo event generators out there. The first are general purpose Monte Carlo event generators, and there are three major ones. So Herwig, Pythia, and Sherpa. Each of them has their own strengths and their weaknesses as well. For example, Sherpa, very good at doing phase space integration, very good at doing next to leading order calculations in an automated fashion. Pythia, very good at doing the soft side of things. So it's able to do really nice soft QCD, multi-parton interactions, and the string model itself also is a strength of Pythia. Herwig, very good all around. The ability to do different types of parton showers, also the ability to do cluster and string models for hadronization as well. So they all have their strengths and weaknesses, and it's very good that they all exist because it allows you to compare the results that you get from one to the other, because I can tell you right now that all of these have bugs. The question is, how severe of bugs? As an example, in Pythia, we just did a release of Pythia about 2 weeks ago, Pythia 8.315, where we fixed a bug that was there since Pythia 8 came out, which is something like 2000, I'm going to get this wrong, something like 2006 or something. And it's been there since the beginning in the Lund string fragmentation model. So these bugs are there. They can be there for a long time. So it is critically important that we have other event generators, or that we have a number of event generators to cross-check between things. Okay, so these are general purpose Monte Carlo event generators. What do I mean by general purpose? It means that they can do all of these things here. So they can do the hard process, they can do resonance decays, they can do parton showers, underlying event hadronization, and normal decays as well. So these things do the whole deal all in one go. We then have specialized event generators. These are all the ones in blue. There are a lot of them. So for example, H decay, which is specifically for Higgs, Ariadne, which is a specific type of parton shower, Vincia, which is a specific type of parton shower, actually is incorporated into Pythia now. We have things like FOJET, DPMJet. These really work on underlying event side of things. Then we have hadronization. I put this one in here. This is a specialized version of it, MLHAD. So this is a machine learning model that we have to do hadronization. There are other types of dedicated hadronization tools out there. And then in terms of decays as well, there are a number of decay tools out there. TauLa, which does tau decays, EVTgen, which does B decays. So there are any number of tools out there. They all have their specific purposes. In terms of hard processes, there are also things like PowHegBox or MadGraph or other tools like that. So what goes into all of this in terms of, we have this event generator, what do we do with it now? Well, it's not really just an event generator because there's an entire chain that it goes through. So on the left-hand side of this plot, we have what I'm going to call real life. So what happens at an actual collider experiment, whether it's CMS or Atlas or LHCb or whatever. And on the right, we have our virtual reality. So what happens with the Monte Carlo event generator? So in real life, the machine, in this case, let's say the LHC, collides protons and produces events. In the case of Pythia, let's say we have these proton beams where we have the event generator. It then produces all of our particles that will be seen in the detector. The machine produces events where those particles will be seen in the detector. So then what happens? We observe and we store these events. So in the case of the experiments, this is actually really quite complicated. We need to have triggers where we can actually filter the data, get it down to reducible levels. We then store it, and then we reconstruct it. So on this side here, what we have is data acquisition, and we have the detector. So the detector actually measures the event. The data acquisition allows us to store the event. On the Pythia side of things, or the event generator side of things, we just have detector simulation. So something like GEON, where we take these particles, we pass them through a material simulation for that detector, and then we look at the output that we get from that. So what it would actually look like in our detector components. Let's say that we have an eCal in our detector. Well, here, the detector observes some sort of EM shower. Here in the detector simulation, let's say we have a very hard photon hit that virtual eCal. It then simulates that shower that EM shower in the detector simulation. Once we have this, though, this split between real life and event generator comes together. We then can have event reconstruction, and we have physics analysis as well afterwards. So this event reconstruction can work just as easily on real data as it can on detector simulation, hopefully, if you've got your simulation chain set up correctly. So this is really kind of the second point that I had on that list of why event generators can be so important. It's because we can reproduce all of this right here, so we can actually know what the kind of ground level of what the generator is producing. Whereas here, with nature, we don't actually know if it's a Higgs or not. Whereas with a Monte Carlo generator, we do. So this is really quite a bit of power behind Monte Carlo. I want to give an example of the detector side of things because I think while we're really going to delve heavily into the Monte Carlo side, I think it's important to keep in mind the detector side. So this is an example from an analysis that I did a few years ago, now quite a few years ago. And this was, we looked at the production of J-psi mesons. So this is a CC bar state. And we looked at the decay into muons, so a mu plus and a mu minus. And then the thing that was kind of interesting in this analysis was that we looked at the production of these J-psis in a jet. So a jet being a clustering of particles in the event. So jets, the nice thing about jets are that they are accessible both on the parton side. So if you have an event generator that produces partons without hadronization, you can cluster those partons together. And in the detector side of things, the experimental side of things, you can also still do that clustering with the observable particles that you have. And in principle, it should give you something that's one-to-one between the two. So the idea is that we looked for these J-psis by a mu plus and a mu minus, and then we looked at them in jets. And then what we did was we measured this momentum fraction, this z, which I realize we're going to use this variable z in other tutorials. This is not the same z as that, but it is roughly similar in the fact that it gives you a momentum fraction of the thing that you're interested in, this J-psi, in this case it's the PT of the J-psi, over the PT of the jet. So the idea is that if you have a J-psi that doesn't have anything around it at all, that you're going to have a peak near 1. And if you have a J-psi that has a whole bunch of stuff around it, it's going to peak near 0. And if you have a J-psi where there's some stuff around it, it'll peak more in the middle. And this is the result that we ended up getting here. So this is this ratio here. This ratio goes from 0 to 1. This is a very isolated J-psi. This is a J-psi that's not isolated at all. We have two results. The first, are these black data points. This is an LHCb measurement. The link is here. So this is the actual experimental measurement that we made. We made a prediction with Pythia, which can generate Porconia and can generate the J-psi. And this is the result that we got from that. These two are not even close to each other. Okay, so why is this important? Well, it turns out that when you reconstruct this final state, both the jets and the J-psi, you want to be able to unfold your detector resolution. So in other words, if your detector doesn't always see muons, you want to make sure that you can correct for that. If your jet energy scale is way off, so if you measure only 50% of your jet energy, you also want to be able to struct for that and handle for that. And so if you have some sort of event generator like this, which is not actually giving you a good description of your data, it means that when you are trying to correct for these kind of effects in this result right here, it can be highly problematic. So let's talk about those two efficiencies that we have. The first is that we don't reconstruct the muons at 100% efficiency. And so if we were to look at the pseudorapidity of the muon on this axis here, LHCb is a forward detector, so that means that the pseudorapidities go between 2 and 4.5. And if we were to look at the momentum of the muon on this scale here, so this is in GeV, then what we see is this is now a color map of the efficiency. Red means 100% efficient. Purple means 0% efficient, so we don't see it at all. White means we can't see anything at all. What we see is that there's a large portion of space where we're very close to 100% efficient, but there are other places that we're not. So if we're not able to account for this correctly, then this distribution might have some sort of problem in it. To get this distribution, we have to use data techniques, but we also need to use simulation as well. So this is kind of the first effect. The second effect, and sorry, this is what this effect looks like. So this is what our raw data looks like, blue. This is what our efficiency corrected data looks like using Monte Carlo. You see that there's already a relatively interesting shift, that we get some sort of shoulder over here that we didn't see before. Bless you. Okay, this isn't even the biggest effect. We also can't measure the PT of that jet very well. As a matter of fact, the resolution isn't particularly good. So the idea is that we do this thing called unfolding, where we basically go from our observed kind of histogram that we have. We then can say that is equal to some sort of transformation matrix times what originally we had. So this is the process that we call unfolding. We invert this matrix and we say, okay, we can figure out what our original distribution looked like if we apply this transformation matrix to that observable. The way that we get this transformation matrix is we understand what the detector resolution looks like for jets. So what does it look like? Here, this gives us on this axis, going up this way, the z of the j psi, and this is then reconstructed and this is generated. So you can see here that in this PT range of jets, we have a relatively good central value, but we also have a relatively large spread here. As we go to higher energy jets, you see that we don't actually even have that good of a calibration and that we have this kind of shift off of diagonal. So this actually makes a relatively large effect. So when we apply this type of detector unfolding, we go from this red distribution, which was the efficiency corrected distribution, to this black distribution here, which is the unfolded distribution. So effectively, we went from, well, I don't have the plot to show, but we went from a distribution that kind of looked like this to a distribution where we actually have this shoulder emerge. So why am I showing this to you? It's because this requires Monte Carlo, and this requires Monte Carlo, typically. And if you don't have Monte Carlo, or if you don't have good Monte Carlo, it is very hard to do this well and to get good uncertainties on it. And in this particular case, we had a huge amount of problems with the Monte Carlo, because this is roughly what our measurement was looking like. This is what Pythia was giving us. For us to be able to do this unfolding, we actually had to go do a home-cooked kind of generation of this Monte Carlo to get this unfolding matrix out. So it turns out that it is critically important for these types of studies to make sure that you have good Monte Carlo. Okay, so if I go back all the way to this slide here, we've covered now the connection of perturbative and non-perturbative regimes. That's this whole kind of setup that I gave you of connecting these things all up. This then provides us complete events with final state particles, and this is why it's important in terms of things like unfolding. The last thing that we're going to talk about is robustly performing high-dimensional integrals, which seems like it's a bit of a departure from everything that we've talked so far, but it is really quite important. Otherwise, we wouldn't be able to make any of these predictions at all. So you go here. Okay, so let's talk about ways that we can do integration. So ideally, if we do integration, we just do integration analytically. We can write it down. We can say this is the integral, done, right? Or if we can't do the integral, we put it into Mathematica. Mathematica does the integral, done. Or if Mathematica can't do the integral, you ask someone who knows how to do integrals really well, done, right? But sometimes that's just not possible, right? You can't get an integral out. Particularly if you go and ask someone to do something like a 32-dimension integral, they'll probably say, no thanks. Okay, so that means that we need to have numerical methods for doing integrals. And kind of the first one that you might think of is, okay, I have a one-dimensional distribution. That one-dimensional distribution is given by this red line here. In this case, this is something like a fourth-order polynomial, of which I've taken a bit of it out. Okay, so you say, I want to integrate it over a specific range. So I want to integrate it from point A to point B. And you say, okay, I can approximate this integral. And the way that I can approximate this integral is I look right at the middle of this function. I say, okay, I'm just going to draw a line across. I know how to calculate the integral for this constant number here. Yeah. So I can say my integral is just going to be approximated by the area under this black box. And that's just going to be given by this here. So that's the first way that you do it. And you can say, well, okay, this is not a particularly good integral. Can I do a better job? And you can say, well, yes, I'll split this up into points, more points, and I'll calculate a box for each of these points, and I'll add them all up, and I'll get the integral. And if the integral isn't coming out enough, I'll put in more points, and I'll put in more points, and I'll put in more points. I'll put in n points until I get an integral that is good enough for my purposes. And the way that I can evaluate whether that integral is good enough for my purposes or not is I say, well, what happens when I do the integral here using just one box? And what happens when I do it with two boxes? Is that percent change an acceptable percent change for me in the integral? So this is just a generic quadrature method, and this is specifically the midpoint method. We can do a little bit better. You can say, well, maybe this actually isn't the best estimation of what my function will look like. Instead, let's do it with something like a trapezoid. I can calculate out what the area under a trapezoid is, no problem. So I still have the same function. But now, for my integral, I'm calculating out the integral under the trapezoid, which gives me this number here. And don't worry, you'll get to implement all of these code in one of the tutorials, I think, not tomorrow, but the one after. Okay, so trapezoidal method. Then you could say, well, that's not even so good. Let's do something better. Let's do some better interpolation. So if I were to say this, right, this is a constant interpolation. This is a linear interpolation. This is then a quadratic interpolation, which is Simpson's rule, where the idea is that you take some sort of polynomial here, and then from that polynomial, you can then calculate out what this integral is. And you might do even slightly better with this as well. And so when you do that, you get some sort of formula out like this, and you can say, well, I can go to whatever order I want in the polynomial that I'm using for this interpolation, or I can use other interpolation techniques where I have different boundary conditions, which allows me to approximate this integral numerically even better. Okay, so all of these methods are relatively straightforward, and they work very, very well in one dimensions. If you want to go and integrate a function in one dimension, then using some sort of quadrature method is probably your best bet. Now, there are caveats to that. Specifically, if you have some sort of divergences in these, you need to be very careful about how you do that. But in general, this is probably the way that you want to go about calculating that integral. But there's another way to do it, and that is Monte Carlo integration. So the idea is that you're still trying to do this integral here. You're still trying to do it over a bounded area, so from A to B. And you have your function f of x. And what ends up happening is that this integral here of this function can be approximated as the average value for f of x, if it is uniformly sampled over x, times then the area over which you're integrating. So in this case, from B to A. So I take this average value that I get out and I multiply it by B minus A. And so I can write that here as an integral over the volume, and we can approximate that as this average value of f of x, where these are uniformly distributed random numbers in that volume, times this volume here. And we'll do this in one of the tutorials as well, so I won't spend too much time here. But here's a little bit of Python code here, which allows you to calculate pi in something like 5 lines maybe. There's some line wrapping here. The way that you do it is that you throw random numbers between -1 and 1 and -1 and 1. You see if it falls within the circle or outside of the circle. You calculate your average value. That will then give you the area of this circle, and from that you can calculate pi out. So this is a very powerful technique to go and do it. This converges relatively slowly. It is not a super fast way of calculating pi. There are faster ways to do it. But Monte Carlo turns out to be dead simple. You just have to do this. You choose a volume to integrate over. It can be in 1 dimension up to n dimensions. You calculate out your average function in that dimensionality, and that's it. you're done. You'll notice with this, there's no grid that you need to set up, so you don't need to sample endpoints. You sample as much as you want till you get the precision that you want. If you don't have the precision you want, you can keep on going later and pick up where you left off with your integration. That's something that you can't do with these quadrature methods. Okay, so how do you speed some of these things up? So I already talked about this adaptive quadrature, the idea where you can subdivide this space until you get the necessary accuracy achieved. This doesn't actually speed things up. It makes things more accurate, but it slows things down. The way that you can speed up this adaptive quadrature is you can do stratified sampling, which is similar to MC, or sorry, is similar as above, but for MC integration, where you basically take your function and split it up into little volumes. And then you can take those volumes and you can integrate them as you need to. So let's say there's a place where you have a divergence in your function. You can have a very small volume for that, where you do a very detailed number of these points in that volume. And let's say you have one where the integral is really quite easy and you don't have a large variance, then you have a relatively large value for that. So this is the idea of stratified sampling, which can make the convergence faster. And then finally, you can do this thing where you do this importance sampling, where the idea is that you take whatever function you have and you, in your volume, and you actually apply random sampling that isn't uniform, but rather a random sampling that has to do with the shape of the function that you have in that volume. This might not be so clear from what I talked about here, but we'll get to it in just a second in a little bit more detail. So before I get into this, I want to give a few comparisons for some of these techniques. So we're going to assume baseline algorithms. So this means no adaptive, no stratified, anything like this. And what we're going to say is that we're integrating with d dimensions and we're sampling n times. So what do I mean by that? If it's a one-dimensional plot or one-dimensional function, then that means d is 1. If we sample n times, for example, with a quadrature method, that means we're taking n points and then we're evaluating that block of the integral for those n points, whether it's a trapezoid or just a block or some sort of interpolation. If it's for the case of Monte Carlo sampling, this n corresponds to the number of times that we've generated a uniform random number. So that's what this is here. Okay, so the methods that we have, trapezoid, Simpson, Monte Carlo, I don't give the midpoint rule here. But what you see here is that these things scale with this convergence in terms of the number of dimensions very, very poorly. So as you increase the number of dimensions per step that you're taking basically here, these things converge very, very slowly, whereas Monte Carlo converges very quickly. So this gives us, hi.
Usually we can want you to close the door. If you want it open, I can just call and let them know, but.
I think we do want it open.
Yeah. Yeah, I can just call and let them know if you want it open. Yeah, we probably close it now. I think we got it by the end.
Sure, yeah, I leave it up to you, Fred. Go ahead and, yeah, we can close it.
Okay, appreciate you, thank you.
So you see here that as we go to higher and higher dimensionality, this is where Monte Carlo shines. But as we go to low dimensionality, it turns out then that really the trapezoid rule here, or sorry, as we go to higher and higher sampling, we have this factor here. But then as we go to higher and higher dimensionality, we have this arise here, which is problematic. So that means that for Monte Carlo, we don't have this dimensionality scaling at all, which is great. So why is this important for us? Well, when we work with high energy physics, it means that we're working with quite high dimensionality. If we want to calculate something like a 5-jet final state, we need to integrate over quite a high dimensionality for that phase space. Okay, so let's talk about random numbers now, because in all of this Monte Carlo, this n corresponds to the number of times that we have sampled. So how do we do that? Well, we use random numbers. And this is why we're going to spend an entire tutorial on random numbers, is because they're critically important for all of this. So true randomness, this is what we see in nature, or at least this is what we think we see in nature. Pseudo-randomness is what we get from computers typically, which approximate true randomness, but it really is deterministic. But in principle, we don't necessarily know the determinism behind it. So for example, the lotteries that are typically thrown, those are usually pseudo-random. But it's critically important that no one knows the true pattern behind it, although people can sometimes figure it out. And then there's quasi-random, which is like pseudo-random, but sometimes you want to have a more uniform distribution of what things look like. And so we kind of have this Venn diagram of the characteristics of these things, where we have pseudo-random, where things are independent, and we have true random, where things are unpredictable. Pseudo-random, it's predictable because if I know the random number generator I'm using, and if I know then the way that I'm doing it, my initial seed, I can then reproduce that pseudo-random generation. And then we have quasi-random sitting over here, where it is predictable and not necessarily independent either. So just to give an example of this, this is what we would call something like pseudo-random, where this is generated with some sort of pseudo-random number generator. And this then is something that's quasi-random, where we actually have a more regular distribution of these points here. And in some cases, this is actually something that you might want. So if we were to look at that kind of original image that we had from Pixar, from Finding Nemo, there you'd want to use something that was quasi-random. For particle physics, since we actually want to get integrals out, we want to use something that truly is pseudo-random. Okay, so what kind of things can we say make a random sequence really a random sequence? The first thing is that it is bounded. So that means that we have some sort of maximum from it. It cannot be easily determined in terms of pattern. So if we look at kind of high-level correlations from it, we don't see a pattern emerge. In the tutorial, we'll see some of these patterns emerge. The moments approach our expectation. So the first moment is just 1/2. The second moment is 1/12, so on and so forth, for a uniform distribution. So these are the moments. And then when we divide it into bins, each bin is Poisson distributed. So these are kind of the general things that we want to have for this. This is what we mean for anything that is random. It's pseudo-random when we have this reproducible sequence. And some of the characteristics that we want is that it's fast to calculate, that we have a very long periodicity, and that it's theoretically validated. And perhaps this last one, which is really quite important, is that it works. So some of these random number generators really don't work. So random number generators seem like a silly thing. It seems like you should be able to get these characteristics relatively easily. Turns out it's incredibly hard to do, and you run into all sorts of problems because of random number generation that has gone awry. So one of those tests, looking for patterns, is called a spectral test, where the idea is that you basically take these pairs of points. So this is your initial point, this is your next point here. And then, you do some sort of spectral test where you look at correlations of these points. This is what's called a linear congruential generator, an LCG. We'll do that in the random number generator tutorial. Turns out that this does not pass spectral tests. So if you look at correlations between points of these, this is actually an implementation of this here, you will get something that looks like this in this two-dimensional plane. So if you look at one random number generator value and the next generated value, you get these patterns that line up. So this type of generator fails this type of spectral test. It turns out many types of generators like this fail spectral tests like this. This is known as the Marsaglia effect. Okay, so can this cause problems? Absolutely. There is this famous random number generator out there called RANLux. It was part of the kind of the standard library that was distributed by CERN, and it used across simulations pretty much everywhere, to the point where it even made it into LHCb simulations, even though it is a relatively old random number generator. But it's used for any number of reasons. Used in LHCb simulation, it's used in modal simulation, but some issues arise. So specifically, we get something that looks like this. So this is a GEONT simulation of particles passing through the LHCb detector. Specifically, this is kind of the beam sitting, the magnet sitting here. And you can see these patterns emerge. This is a clear failure of this spectral test. This came about because we were using a standard CERN random number generator, RANLux. You got to be really careful, because if you're doing something off of this, you're going to get Monte Carlo's total garbage, and it's not going to make any sense at all. Perhaps the most commonly used right now is called the Marseille twister. It does this thing where it uses these Marseille primes. We're not going to talk about that in the tutorial, but we will do bit shift and we'll do bit masking as well. Okay, so that's random number generation. I'm out of time, aren't I? We're flexible? Okay. So I'll go a little bit faster on this, but that's random number generation. That gets us a uniform random number. So in other words, that gives us a distribution that if we were to make a histogram for it, it would just give us a box from 0 to 1. Okay. Usually we don't just want an integral. Usually we want to sample points from some sort of distribution that's not just a uniform distribution. And so that means that we need to be able to sample from these things that aren't just uniform distributions. So how can we do that? Well, let's introduce a little bit of nomenclature here. The first thing is that we have a function that we want to sample. So in this case, f of x. Then we can take the integral of it. So this is the integral of the function to sample. And then we can take the inverse of this primitive. So this f inverse. So capital F is the integral, and then f inverse, capital F inverse is the inverse of this integral. If we have these three components, we can actually analytically go from a uniform distribution to our sampling function that we want, which is f of x here. So the way that we go about doing this is we sample from f of x with a uniform distribution that's bounded along x. So the idea here is that we have this function here, f of x, and we bound it with an x min and some sort of x max here. And then what we can do is we can write out all the math for it. So we can say that the integral from this point here to this value x of the function is equal to then just the integral from x min to x max of this function times this r, where r is a uniformly sampled random number. Then what we can do is we can say, all right, this then gives us the integral at x minus the integral at x min, and I can write it out like this, which just gives me the area that I have of this function here from x min to x max. And so what I can do is I can then solve this for x. And so that gives me that if I have an x here, it is equal to the inverse of the integral of my function times then the integral of my function evaluated x min plus my uniform random number r times a, which is the area of the integral from x min to x max. And depending how well behaved your function is, you can calculate this. Turns out that most functions, you can't calculate this because integrating and then taking the inverse of that integral is surprisingly hard for many of the distributions that we're interested in. But there are some that it is possible with. So for example, here we have just a linear function where we can do that. And here we have something like an exponential where we can do this as well. So the idea is that you calculate your uniform random number, and then you put it through this transformation, and then it will transform it into this distribution that you want. So something that would look like this distribution here. So this is what we call this analytic sampling that we have. You can also do something called bin sampling, which is effectively a numerical equivalent of this, where you say, okay, I actually can't invert this integral. But what I can do is I can approximate it by a bunch of boxes with the midpoint rule, or you can do it with the trapezoid rule, or you can do it with Simpson's rule. But what you will find out is that you need to take the integral of each of these boxes, and you need to take the inverse of that integral, and you quickly get to a point where you can't take the inverse of a fourth degree polynomial, or I should say a fifth degree polynomial, that there's no closed form for it. So usually working with boxes is what we work with. So the idea is that you have this here. Then what you can do is you can integrate it, which is this box down here. So I've taken this and I've integrated it. So this box is just this box here. This box here is this box plus this box here are these three boxes added together. You get the idea. And then we just need to invert it. And numerically inverting it is no problem. All it is we're just turning this histogram on its side. And so what we can then do is we can sample a uniform random number, and then we can get out an x value from that instead. So the idea here is that we sample our uniform random number, we find our corresponding bin, and then we figure out the x range that we have, and we sample from that. So this is a way that we can do with bin sampling. Then we can do something that's called accept or reject sampling. And in accept or reject sampling, the idea is that we have our function f of x, and that we have a uniform sampling of a bounded box or bounded volume around it. So the idea is that we've got this function sitting right here, same function as before. And what we do is we say, okay, this has some sort of maximum. We know what that maximum is. And we say, okay, that maximum is f of max, and we're bounded here on the left side at x min and on the right side at x max. Then we sample two uniform random numbers. The first is between x min and x max. The second is between f min and f max. And we then put that point into this plane, and we say, well, if it falls underneath my function, I accept it. If it falls outside of it, I reject it. That is actually very similar to what I showed you with the circle for the Monte Carlo sampling. And so the idea is that you can go through this process is first you sample an X, second you sample a Y with a second random number generation, and then third you determine whether it's accepted or rejected. And so then you can calculate the integral this way, just number of accepted over number of tried times the area of this bounding box. So this is back to numerical integration using the Monte Carlo method, but here instead of taking the average value, where we actually get a value for this function, we instead have a binary value. So this something like this would converge less quickly, but it allows us to get this distribution out. Okay, we can also do importance sampling, very similar to accept or reject, but now we choose a more efficient g of x, which is this bounding function. So here we chose the bounding function, which was just a straight line, so a uniform distribution. Here we can choose a bounding function which is something like this, which is going to be more efficient in terms of our accept or reject. And so we do the same thing as well, except the difference is for our x, we sample from g of x. For our y, we then sample from our function here as well. And then finally, we do this comparison. We see if this y is greater than f of x. And so again, this gives us the same thing. All we're doing is a more efficient sampling of this space of points for the accept or reject method. Final one here, I think, for these methods that I want to talk about is multi-channel sampling. So this is similar to importance sampling, but now we split it up into a bunch of functions. So we say this function of g of x is now just a bunch of these other functions. So here, for example, you might have these two exponentials, and from these two exponentials, you can sample a function that looks like this. So that's the example here. If you want the details, we'll go over them in the tutorial as well. Okay. I'm out of time, so I'm not going to talk about this. Sampling in time is important. This gives us something that we call this this veto algorithm, and I'm not going to talk about it here, but it's critically important in the case of the parton shower. We'll get into more details about that for the parton shower. I will briefly talk about it here, though, just because we will use it later. So we want to do some sort of importance sampling as a function of time, let's say. So something like a parton shower, which is a function of energy, but same idea. The idea is that we have this function here. And so we end up with this incorrect exponential factor here. And so the way that we go through this algorithm is that we start at some initial time and some increment I. We increment I. We then calculate out a new time. So in other words, we say we're at this new time, given the inverse of this function here. Then we say, OK. We can calculate out what this y value is, and we either accept or reject this point. And so it's effectively accept or reject in a time series. We'll go over this more when we get to parton showers, but this is just something to keep in mind. Winner takes all. This is another way to do it in terms of multiple things, like something like multiple decay channels, which we'll talk about in one of the other tutorials. So a lot of techniques out there, a lot of information on it. Hopefully some of this is sunk in, but all of these techniques are used to build a Monte Carlo generator. Something like Pythia, for example, uses all of these techniques in it. Okay, so I just want to summarize for this. First of all, the reason Monte Carlo really is quite important is it allows us to connect these perturbative and non-perturbative regimes. It provides complete events with final state of particles. It robustly performs high-dimensional integral. Then, some things that are important to remember. Monte Carlo integration and sampling are not the same. So Monte Carlo integration, you get an integral out. Monte Carlo sampling, you get a distribution out that comes from some sort of random, some sort of function that you want a random sampling from. Multi-channel and veto samplings are commonly used. All of the ones that I showed there are used in most of these event generators. And this last one, which I really want to highlight, is make sure you use a good random number generator. So that's pretty much what I want to say, but I want to just go back to the schedule here to highlight where we're going to talk about some of these things. So we're going to talk about random number generators. So we're going to talk about Pythia right after this, after the coffee break. So we're going to go through the Pythia tutorial. Then tomorrow we're going to go through random number generators. You're going to get to see some good random number generators, some bad random number generators, and build random number generators for yourself. Then we're going to do sampling and integration on Monday. And then we're going to do some of the actual implementation for Monte Carlo on Wednesday. So that's kind of where we stand with everything. Questions at all? So that is an inverse CDF, right? Yeah, so that's all that I'm showing here. So the problem, of course, is that you've got to get it's got to be bounded so that you have a CDF that you can calculate, right? But that is the inverse CDF method. So if you're doing this here, that's your inverse CDF right there. For when you're doing integration and things like this? Yes. So Vegas is super. Yeah. So Vegas is very, very popular. So Vegas is an important. Well, so it's an adaptive multi-channel basically. But the idea is that you have really high dimensionality. You then collapse it down to each dimension of your kind of volume. You look for your kind of peaks that you have there, and you set up your importance sampling around those specific peaks. And then you can do this as you go through, and it's adaptive, so it will split these things up further and further. Vegas works really, really well. It's a very good algorithm. In general, it's pretty fast, but even for relatively complex integrals where you have these let's say n-jet kind of final states, it can slow down for sure. Vegas actually works probably better than any expectation for how good it should work, actually. This projection into these along the dimensions of it, it works extraordinarily well for most applications in particle physics, even though it's not clear why it necessarily should. Yes. 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 And when you're working in really high dimensionality, of course, you might say, well, how the heck do I actually divide up? It's hard. But the way that it does it works very, very well. So, yeah.
Thank you again. A couple of logistics comments. Yeah.